Do you guys have a black marker?
Yep.
All right, everybody, we're going to get started. So in the past couple of lectures, we talked about policy gradient algorithms, which are algorithms that can learn policies by directly differentiating the expected reward. And then we talked about how we can use value functions and Q functions to actually improve the variance of the policy gradient estimator. Today, we're going to continue that story by finding some other uses for value functions and Q functions, where we'll actually get rid of parameterized policies altogether and show how we can do reinforcement learning using only value function and Q function estimation. But first, a few logistical notes. So homework 2 is due in exactly 1 week, next Monday. Homework 2 is probably going to be quite a bit harder for many of you than homework 1 was. So homework 1 was sort of just a warm-up to use supervised learning to learn some policies. In homework 2, you'll actually be implementing a proper reinforcement learning algorithm, specifically the policy gradient method that we covered last week. So do make sure to start on that early to make sure that you don't get stuck on some problem and that you have plenty of time to go to office hours and ask the TAs for help. Please remember to start forming your final project groups. Hopefully all of you have already done this, but if you haven't, you probably need to do that very soon because your proposal is due this Wednesday on September 25th. For the proposal, you'll be submitting it through Gradescope, and you'll also be submitting it anonymously to a peer review system where your classmates will actually look at your proposal and give you feedback on it. So we'll have directions posted for that shortly, and the submissions for that will probably open like tomorrow or Wednesday, so you'll be able to get that in. So please do make sure to put in the time to get your proposal looking nice, because that's going to be your main way to get feedback on whether your project sort of meets the scope that we expect in this course. All right, today's lecture. Today, we're going to talk about what happens if you have an actor-critic method and you basically get rid of the actor. So if you just have the critic left, can you actually do reinforcement learning with only a critic? And it turns out the answer is yes. We'll talk about how you can extract a policy from a value function. Then we'll introduce the Q-learning algorithm, which is going to be the main deep RL algorithm that we'll actually discuss in today's lecture. We'll talk about some extensions. This might actually most likely be on Wednesday, so I probably won't get to this today. But on Wednesday, I'll talk about how you can do also Q-learning with continuous actions and some algorithmic improvements. And today, what I'll probably end up concluding on is a discussion of some of the theory behind Q-learning. So the goals for today's lecture will be to understand how value functions can give rise to policies, understand the Q-learning algorithm, and maybe understand some practical and also some theoretical considerations behind Q-learning. All right. So let's briefly recap some of the things that we discussed last week. So last Wednesday, we ended on a discussion of the actor-critic algorithm. And here I have the batch version of the actor-critic algorithm, just like I had it written out on Wednesday to summarize. So an actor-critic it's essentially a version of policy gradient where we also fit another function approximator to the value function, and we use this value function approximator to give us a better policy gradient. So in the actor-critic algorithm, just like in policy gradient, the first step is to sample data by actually running your policy, interacting with the environment. Then we fit a value function. We saw how we can fit the value function in a few different ways, using, for example, Monte Carlo estimates, or using bootstrapped estimates, or doing something like the n-step returns estimator and its variance. So there are a variety of different ways to fit the critic. Then we can evaluate the advantage at every time step and sample as simply the reward plus the next value minus the current value. So this advantage essentially quantifies how much better is the action AI than the average return you would get from state Si. So the advantage of Si AI tells you how much better AI is than the average return you'd expect to get. And this advantage you can basically plug in right into your policy gradient estimator by simply multiplying your grad log pi's by the estimated advantage. And this gives you a policy gradient, which you can then use to improve your policy. So that's the batch mode actor-critic algorithm. We also saw an online version of the actor-critic algorithm where you take only one step only one sample in step one and then perform the update using one step. And then we also saw how in practice you probably want to parallelize this so that you take that one step on a collection of multiple workers so that you can perform your update with a batch size of larger than 1. Okay, and fitting the actor-critic algorithm into our typical anatomy of a reinforcement learning algorithm, the orange box corresponds to step 1, the green box corresponds to step 2, so that's where we fit the value function, and the blue box corresponds to actually applying that gradient. So the question I'm going to ask next is, can we omit the policy gradient completely? So a lot of the trouble that we've been going through so far has been because the policy gradient has such high variance. So all this stuff that we needed to do, fitting the critic, using n-step return estimators, all this business with baselines, etc., all of that is because the variance of the policy gradient is high, and in order to get more efficient and more stable RL algorithms, we need to reduce that variance. So if the variance of that policy gradient is such a big problem, can we just get rid of it altogether? Perhaps we can just use that fitted value function in some way to get us a kind of an implicit policy and avoid having to explicitly perform gradient steps on our policy parameters. So can we omit the policy gradient completely? So the hint about how we can do this is in the definition of the advantage function. So the advantage function, as you recall, is a quantification of how much better is the action, AT, than the average action according to current policy pi. So if you have a good estimator for the advantage function, you can basically answer the question for a given action, how much better than average is that action? So now we can start to think, how can we use something like an advantage function to allow us to get rid of the policy gradient altogether? Does anybody have any ideas? Does anyone have any suggestions for how we could start thinking about an algorithm that doesn't require policy gradient? Any volunteers? Yes, over here.
Instead of improving the policy using the gradient, you could just say like, oh, if a pi of this action is better, just make my set my policy to that, the best action according to A.
Right. So the answer was, well, if some action A has a large advantage, then perhaps you can just force your policy to take that action. So instead of trying to calculate some sort of gradient, just say that my new policy will be the policy that, if it sees state ST, will take the action AT for some AT that has a big value of A. So one way to find an action that has a big value of A is to actually just take the max with respect to the action. So if you take the argmax of the advantage ST-AT with respect to AT, you'll get essentially the best action from the state ST if you then follow pi, right? So remember, value functions, Q functions, and advantage functions are all predicated on a particular policy, so that's why we write them as V pi, Q pi, and A pi. So if you take the argmax of A pi with respect to AT, then you get the action for which you will collect the largest reward if you take that action and then follow pi. So this action, this argmax, will be at least as good as any action that you would get from sampling from your policy. And in fact, it'll typically be better unless your policy is already as good as it gets, regardless of what your current policy actually is. And it's actually pretty easy to show that even though this advantage tells you what will happen if you then follow pi, because you're actually improving the policy at every single state if you do this argmax, following the argmax policy can only do better. So you will not get worse from doing this argmax at all states. So then we could say, well, let's just forget about explicitly representing policies. Let's just do this. Let's say that our policy is the argmax. And all we really need is some way to estimate the advantage. Because if we can estimate the advantage, we can recover the policy using the argmax. And if we use that argmax at all states and all times, then we can only do better. We cannot do worse. So this allows us to define a policy that does not have any parameters, that is defined entirely in terms of an advantage function, and it's just the policy that assigns a probability of 1 to the argmax of a pi and a probability of 0 to all other actions. And I'm going to call this policy pi prime. So pi prime is a policy that always takes the argmax action for a pi. And remember, a pi is the advantage for some other policy. So this pi prime is as good as pi, and probably better. In fact, with a little bit of legwork, which you guys can do as a take-home exercise, you can actually show that pi prime is actually better than pi unless pi is already optimal, in the case where you can get an exact advantage. So now this immediately suggests a new way to design a reinforcement learning algorithm. Again, when we want to design a reinforcement learning algorithm, all we have to do is we have to fill in the blanks, these 3 blanks. So the orange box stays exactly the same. What happens in the green box? Any ideas? Anybody want to raise their hand and yes, back there?
We're just fitting our advantage function.
Yeah, somehow fit something that gives us an advantage function. Fit a v, a q, or an a. So some kind of fit. What happens in the blue box? Any volunteers? Yes, over there? Exactly. You just make your pi be pi prime. So just turn your policy into the argmax. Just assign pi prime to pi. That's it. So no actual learning going on there. Just make this be this. Very simple. So this is a complete reinforcement learning algorithm. And there's a very large class of RL methods, in fact, that are based on this basic recipe. So we refer to these sometimes as approximate dynamic programming methods, value-based methods, fitted value methods, fitted Q methods, and so on. And that's what we're going to discuss primarily in today's lecture. So to get into the guts of how these kind of methods will work, what we need to do is we need to first introduce the concept of policy iteration. Here's the high-level summary of policy iteration algorithm. It's basically going to be this thing. The policy iteration method consists of the following steps. Step 1, evaluate the advantage for your current policy pi. So figure out a pi somehow. And again, there are a variety of ways to do this. You can get v pi, you can get q pi, and we'll talk about those options today. Step 2, set pi to be pi prime. So step 1 is figure out which actions are good. Step 2 is take the good ones. And it's called policy iteration because you iterate between evaluating your policy and then improving your policy by basically setting it to be the best one you can get from your current advantage. And of course, pi prime, as I said before, is just the argmax policy. So you repeat this process. And of course, the important question in policy iteration methods is how do you do step 1? Because step 2 is easy. Step 2 is an argmax. So the main thing we have to figure out is how do we do step 1? And that's where there are a few interesting decisions to be made that will strongly affect the kind of situations that our algorithm can actually handle. So our trusty tool for doing this, as before, is going to be the ability to decompose the advantage into a current reward, a next value, and a current value. So the advantage is given by the difference between the q value and the value, and the q value decomposed into the reward, plus the expected value of the value function at the next state. So this is all the same as last week. And this is what we're going to use to actually allow us to derive a variety of different policy iteration methods. So let's start with the same thing that we did last week. Let's evaluate v pi of s. So we saw how we can fit v pi of s. There are a variety of ways to do this. We know that if we have v pi of s, we can get a pi. So let's go with v pi to start with. And this is going to result in classic dynamic programming algorithms. So first, I'm going to make some unreasonable assumptions to derive basic dynamic programming algorithms that do not work under kind of traditional reinforcement learning settings, but do work if you basically know everything about how the world works. So the first assumption we'll make is that we actually know P of s prime given s comma a, which means that we essentially know everything about the transition dynamics of the world. Typically, we don't know this, but let's just pretend that we do. And then I'm going to assume that both s and a are discrete and small, which again is usually not the case. And s and a being discrete and small specifically implies that we can build a table with a number for every value of s and a. So you could imagine that we live in a small little grid world kind of environment where the agent gets to walk around this grid, so they go left, right, up, and down. And this grid world environment has 16 states, 4 by 4, and in each state you have 4 possible actions. So fairly small environment, you can tabulate everything. That means that you can store the full v pi of s in a table tractably. It's just an array with 16 numbers in it. It also means, so you can visualize them like this. They're basically a numerical score associated with every square. And it also means that your transition dynamics, your P of s prime given s comma a, can be fully defined with a 16 by 16 by 4 tensor. So remember how I talked about the transition operator the week before last? Well, there's your transition operator. It just has 16 by 16 by 4 numbers in it. OK, so this is what we'll work with, and then we'll see later on how we can relax this assumption. So now let's go back to the bootstrapped update that we saw in the lecture last week. So in the lecture last week, we saw that we can estimate a value by taking the reward and adding to that reward the expected value of the value function at the next state. And here, I'm writing everything out in terms of expectations. So we're not doing any sampling at this point. So that means that I have an expectation over the next state. I also have an expectation over the current action. Before, we didn't have this because we just assumed that we were sampling actions from the current policy. But now let's write that out and let's make it explicit. If I really want to define the value function for a policy pi at state s, I need to take an expectation with respect to the action for that policy. And I need to take an expectation with respect to the next state I'm going to get. And then I can plug in the v pi for the next state. So this is the equation for v pi of s. And of course, if I don't know what v pi of s prime is, I can just plug in my current estimate into that and iterate this process until it converges. So that will give me a value function. And I know that my policy on the previous iteration of policy iteration has been updated with this argmax, right? So before, I chose pi prime to be this argmax, and that's what the current pi is. So that means that my policy, whenever I do policy iteration in this way, will always be an argmax policy, which in particular means it's always going to be a deterministic policy. So that allows me to simplify things a little bit, because this is an expectation where a is sampled from pi, but pi is always this argmax thing for some previous advantage function. So I can equivalently rewrite it as a deterministic policy. In general, the policy is, of course, a distribution, but I'll just use this, I'll overload the notation and say that pi as a function of s just gives me the argmax action, just for notational convenience. And then this bootstrapped update simplifies a little bit where I just plug in pi s in there. So even though I have this expectation on the outside, I know that there's exactly one action that has a non-zero probability, so I can just stick that right in there and get a slightly simpler expression. OK, so that gives me an equation that I can use to update my value function. And if I iterate this equation, I'll actually get the value function for v pi. And we'll discuss sort of some of the theory behind that later on in today's lecture. OK, so this is a basic dynamic programming approach to getting v pi if you know everything about your system. Does anybody have any questions about what's going on here? Yes?
Do we lose something from moving from stochastic policies to deterministic policies?
The question is, do we lose something when we decide to give up on representing stochastic policies and start dealing only with deterministic policies? It's a very interesting question. It turns out that you can actually show that for any fully observed MDP, there exists a policy that is optimal and deterministic. That doesn't mean that only deterministic policies are optimal. There may also be a stochastic policy that is optimal. It's very easy to see this. If you have two actions that have the same Q value, then you can randomly choose between them and it doesn't matter. But there always exists a policy that is deterministic and optimal. This is not true for partially observed MDPs. You can actually concoct partially observed MDPs where stochastic policies will do better than any deterministic policy. It's also not true for games. So it's pretty easy to construct multiplayer games where stochastic policies will beat any deterministic policy. But for fully observed MDPs, there always exists a deterministic policy that is optimal. Any other questions? OK. So can we do policy iteration with dynamic programming? Yes. Let's plug it in. So step 1, evaluate vpi. How do you evaluate vpi? By repeatedly performing this, by repeatedly setting vpi to be this, and then chugging along. So that's step 1. And then step 2, set pi to be pi prime. What is pi prime? Well, pi prime is the argmax of A. And how do you get A? A is r plus the expectation of next v minus the current v. And then you repeat. So the policy evaluation step, step 1, that just consists of applying this equation repeatedly. So do this multiple times, and you can actually prove that this operation will eventually converge to vpi. So you can do this quite easily if you have knowledge of the transition operator and a small state and action space such that you can actually represent your vpi in a big table. OK. So this is a policy iteration. We can construct an even simpler dynamic programming procedure if we note something about this argmax. So in a sense, the procedure I had outlined up here, you can view this as a procedure that repeatedly improves the policy. You can also view it as a procedure that repeatedly improves your value function. So it evaluates the current policy, then makes the policy better, then evaluates the value of this better policy. So one way to look at it is that you're moving towards better and better policies. Another way to look at it is you're moving towards better and better value functions. That is to say, value functions for better and better policies. And in order to evaluate the value function, all you really need is you need to know the value of the latest policy. And in some sense, maybe you can imagine skipping the middleman. Maybe you can imagine even skipping this step 2 altogether and just improve the value function directly. And that'll give us an even simpler dynamic programming algorithm. So here's how we can get to this. So first, let's look at this argmax of A. So this argmax of A gives us the best action according to the current value function, where we use the value function to construct A. So here's A. All it's made up of is the reward and the value. Now, we know that the argmax of A is actually equal to the argmax of Q, because Q and A only differ by this term that we're subtracting, and this term that we're subtracting depends on the state and does not depend on the action, so it does not alter the argmax. So we could just as well write pi prime as the argmax of Q pi, which will let us get rid of one of those terms. That's a little bit simpler. And now let's imagine what this argmax of Q actually looks like. We can construct a table where there's an entry for every state and every action. So for every state and every action, we have a number, and that number is our current estimate of QSA. When we take the argmax with respect to A, we're essentially picking the entry in every row that it has the largest numerical value. And we're outputting the index of that entry as our argmax. So that becomes the policy. So then we could ask, well, what's the value of that action according to your previous value function? Well, the value is simply the number that's in that table. So the index of the entry in that row gives you the best action. The numerical value in that cell in the table gives you the actual value. So if you want the max of QSA, if you want the value of the best action, all you have to do is just take the number under that yellow square And that approximates the new value of this new policy that takes the argmax action. Of course, it might not approximate it very well just yet because you need to iterate the process multiple times, but it gives you a pretty decent starting point. Specifically, that starting point is the value you would get if you take the argmax action and then follow your previous policy. So this gives us a hint about how we can actually skip the policy update step and just compute the value directly. And that will allow us to shorten this dynamic programming algorithm from 2 lines to 1 line. So I have it written out in 2 lines, but you'll see how it can be written in 1 line later on. So this is known as the value iteration algorithm. The value iteration algorithm essentially just skips the explicit policy representation altogether and just alternates between building this table of Q values and then setting the value function to be the max along the columns of the table. So you first build a Q function, which you build by taking the reward and then adding gamma plus the expected value of the next value. And then you build your value function out of that Q function by taking the max along the actions. And then, of course, you can imagine I can take this max and stick it up here and turn this into a 1-line algorithm. So the procedure is very, very simple. Build your Q function table, and then set your new value function to just have the value of the largest entry in every row. That's value iteration. So if we were to plug the pieces of value iteration into our favorite diagram, then the green box would basically amount to constructing this Q function table. The blue box would amount to taking the max. So the max is what actually alters your implicit policy, in effect. Does anybody have any questions about value iteration? Yes?
Can I explain once again why argmax A pi is the same as argmax Q pi?
Why is argmax of A pi the same as argmax of Q pi? So the advantage function is defined as the Q value minus the current value. So this R plus gamma expectation of V pi S prime, that's the Q value, and then the V pi of S, that's the bit that's being subtracted. Now argmax with respect to A is influenced only by the parts of this equation that actually depend on A. And since this bit that I'm subtracting does not depend on A in any way, it does not alter the argmax. Any other questions? Yes, back there.
In our argmax table, why are there a couple columns where there's 2 actions highlighted? Are those just like where there's 2 actions that have equal key value? Or?
Right, so the question is about this picture here. So this picture here represents the Q function. Every row in the table is the Q value for the same state but for different actions. And every column, I guess, represents the Q value for the same action but different states. So because we take the max over the actions, we'll pick exactly 1 entry in every row, but we can, of course, pick multiple entries in the same column because different rows just correspond to different states.
Okay, thanks.
Question here?
Under what conditions can we assume that this will converge to the optimal?
Right. The question is, under which condition does value iteration assume to the under which conditions does the value iteration converge to the value function for the optimal policy? The answer is that it will always converge to the optimal value function if you have a tabular representation, meaning that you store all of your values in a table and you exactly represent the value for every state without any function approximation. Yes, back there.
So then what happens if you want to, because it seems like the table is really only for discrete actions and discrete states, so then what happens if you want to continue?
Right, so the question is what happens if you can't build a table, maybe because you have continuous states and actions, or maybe you have a very large number of states and actions. We'll find out at the end of today's lecture, so I'll leave you on a cliffhanger for that. Any other questions? Okay. So actually, we'll start getting at this question right now. Fitted value iteration. So far we talked about these tables. But now, of course, let's actually talk about this question. How do we actually represent V of S? So the big table has 1 entry for every discrete state. So you can literally just write it like this. For state 0, you have V of S equals 0.2. For state 1, you have V of S equals 0.3, et cetera, et cetera. But now let's say that I want to use my algorithm to learn how to drive a car in a racing game from image observations. Now, how many possible images are there? Well, let's say this is a 200 by 200 image, and each pixel can take on one of 255 values for each of 3 colors. Then the total number of possible images I have to deal with is 255 to the 3rd power to the 200 by times 200 power, which evaluates to a very large number, a number that is larger than the number of atoms in the universe, and there's no computer that can hold a table big enough. and even if it could, it would take me forever to actually update that value function. So this is known as the curse of dimensionality. The curse of dimensionality says that with dynamic programming, you're going to get into a lot of trouble if you have any realistically large problem, because the number of entries you have to store in your table will increase exponentially as the dimensionality of your problem increases. So you could imagine that this problem has a dimensionality of 3, because you have the color channels and the width and height of the image. So already you're getting into completely intractable territory. So, of course, what do we do in deep learning when we can't represent some complicated function in a table? We represent it with a neural net. So instead of having a big table for v, we're going to have a neural net function for v, which is going to be a function approximator. It's approximating a function that maps the set of states to real numbers. That's great. Neural nets are wonderful at mapping things to real numbers. So let's see how we can do that. That's our neural net. It has parameters phi, and we can do something similar to what we did before for actor critic. We can train this neural net via supervised regression by constructing training data where inputs are states and outputs are estimated values. How do we estimate our values? Well, we take our Q values from before and we take the max with respect to actions. So you can actually do something like this. This gives you what is called a fitted value iteration algorithm. So in a fitted value iteration algorithm, in this version, I'm still going to say that there's no sampling. We can still enumerate all the states. I realize that's unrealistic if you have too many, and we'll get rid of that assumption shortly. But for now, let's assume you can enumerate all the states. You can go through all the states, compute their Q values, take the max of those Q values over the actions, use those to construct your labels Y, and then solve a supervised regression problem to regress V phi of S onto Y. Okay, now the job ahead of us now is to take this basic recipe and turn it into an algorithm that does not require enumerating all possible states. Because in DeepRL, we like to work with samples. Maybe we have infinitely many states, or far too many to actually list all of them. So we'd like to have an algorithm that works on sampled states. Question, yes?
So let's say we didn't want to use a neural network. Is there a way to skip the table and maybe like approximate like a polynomial function or something else?
Yeah. So the question is, well, can we approximate it with a polynomial function or something else? So v subscript phi can be any function approximator. The derivations that I'm going to show will hold for any parametric function approximator, which includes any polynomial, any neural net, anything of that sort. You can also use non-parametric function approximators. So anything that can basically solve this argmin problem can be used. Now, can be used means that you can code it up and you can plug it in there. A more important question is, can it be used in a way that actually converges to the right answer? That's a much more complicated question, which we'll get back to towards the end of the lecture. Any other questions? Yes? Are we still assuming that we know the transition probabilities? Yes, we are. We will attempt to get rid of this assumption shortly. Okay, so in order to turn this into an algorithm that we can actually use, we need to not have to enumerate all the states. We also need to get rid of the assumption that we know the transition probabilities. So to get rid of the need to enumerate all the states, what can we do? Well, we can sample. So actually, just looking at the form of these equations, nothing here actually requires us to list out all the possible states. So we could just as well have a sample of states, and the same exact procedure will hold. All we need is we need to have these SIs. We need to be able to try every action from every one of those SIs. That's a fairly strong assumption. And we need to know the outcome for every one of those actions. That's also a fairly strong assumption. But at least we don't need to enumerate all the states. So that already means that we could imagine applying this algorithm to things like that car racing game, because we could just sample a collection of images. We don't need all possible images in there. Okay, so what if we don't know the transition dynamics? Well, first, here's a short quiz. Where does this algorithm require us to know the transition dynamics? Like, why do we need to know the transition dynamics to do this? Yes, over there. S prime, yeah. So notice how in here we have a max over AI. So if I just sampled a collection of trajectories, I couldn't actually evaluate this max, because this max requires estimating the value inside the max for every possible action, which means that you have to try every possible action from all of your sampled states. So you don't need to enumerate all states, but you do need to enumerate all actions from every one of the states that you sampled. And this requires essentially being able to rewind time, go back to that state repeatedly, and try every possible action. And that typically requires knowing the transition dynamics. So this is the troublemaker. We need to know the outcomes for every possible action we might take. So what we're going to do next is we're going to do a little bit of a trick to get rid of this assumption. So let's go back to the policy iteration algorithm, because that was a little simpler. So in the policy iteration algorithm, before I had it written out as step 1, evaluate a pi, but we saw before that argmax of a is the same as argmax of q, so I could just as well say evaluate q pi, and then step 2, set pi to be pi prime, where pi prime is given by my argmax, where I'll just write the q here instead of a, just to keep it simple. So how can we do policy iteration without knowing the transition dynamics? That one we can actually figure out. So here's the trick. The trick is to change how step 1 works. So before we said that for step 1, for the policy evaluation step, we'll iterate on the value function. So we'll take the value function and we'll set it to be the reward plus gamma times the expected value at the next state. But let's not do this. Instead of iterating on the value function, let's iterate directly on the q function. So instead of storing a number for every state, we'll now store a number for every state and action. And then we'll just keep turning the crank on this. So we'll just say that the q value at a state SA is the reward plus gamma times the expectation over the q values at the next state. And the expectation now, if your policy is deterministic, you just plug in the policy. If your policy was stochastic, you would take an expectation with respect to the policy too. But fortunately, our policies are deterministic here, so this is all very easy. Now, seemingly, this shouldn't really change anything. And in fact, for policy iteration, it doesn't really make a difference. But now that we see that we can do policy iteration in terms of these q function tables instead of value function tables, now we can do the same trick as before, skip the middleman, but keep the q function updates. And that will actually get us an algorithm that does not require knowing the transition dynamics. So the q function can be fitted using samples, and we can do this max trick again. So remember, before, what we did is we took our policy iteration with the value function, and we said, let's skip explicitly representing the policy and just stick in a max over a into our value updates. And this gave us an algorithm that did not require explicitly keeping track of the policy. So now, let's go to our q function version of policy iteration and do the same thing. So can we do this with q values also, and this time can we do it without knowing the transitions? So this is our fitted q iteration algorithm. So in the fitted q iteration algorithm, we've transformed the policy iteration with q into a fitted value function fitting method, only now we're fitting q functions instead of value functions, which means that we don't need the max when we evaluate the y's. Right? So notice that here there was a max that required us to try all different actions. Here, there is no max. There's a catch, though. There is still a max. It's just hiding. Can someone tell me where the max is down here? Something needs to be maximized. If nothing is being maximized, then nothing is being improved. So somewhere in here, I'm keeping track of my q function, and somewhere in here, something is getting maximized. Where is it getting maximized? Yes, back there. In the v of si prime, right there. What is that v? I'm not learning a v, I'm learning a q.
Oh, the v is still the max of the q values on the action.
Exactly. The v is still the max over the actions of the q value. So the max is hiding right there. There's my max. I'm going to approximate the expected value of v of s prime by taking a sampled next state. So this requires me to sample a transition. I'm going to approximate the expectation with a single sample, si prime. And then to get an estimate of the v, I'll just take the max over all possible actions at si prime. This max does not require me to try every possible action through my dynamics. It just requires me to plug every possible action into my q function estimator. So this does not require knowing the dynamics of the system. This just requires knowing q phi, which of course I would hope that I know because that's exactly what I'm learning. So just by moving the max from out here to in there, we've gotten rid of the need to know the system dynamics. Now all we need is to learn q phi in place of v phi, and then recover the v from the q by maximizing over all the actions, which literally amounts to just plugging different actions into your function approximator and see which numbers come out. Question?
How to deal with the setting where the actions are continuous?
How do we deal with a setting where the actions are continuous? Well, learning a Q function that's a function of continuous actions is actually no big deal. The big deal is doing the maximization. That maximization corresponds to an optimization problem, which can be solved in a variety of ways, which we'll discuss on Wednesday. Yes?
Isn't a one sample estimate for expectation pretty bad?
Isn't a one sample estimate for the expectation pretty bad? So in particular, this is an expectation of v of si prime, and this is an estimate of that expectation using one sample, specifically the si prime that you actually got. Yes, that can be quite bad. So one would hope that if you collect lots of data, the badness of that estimator will average out. But this is absolutely an egregious approximation. Unfortunately, the best we can do if we can't sample multiple outcomes from a single state action tuple. Any other questions? OK. So this doesn't require simulating different actions. It just requires fitting a Q function. So at the cost of having to fit a function approximator in terms of both states and actions, we've gotten rid of the need to know the dynamics of the system, which I would call a pretty good trade. So this method works even for off-policy samples, unlike actor critic. This is somewhat of a delicate point, which I'll discuss a little bit more after the break. But you basically don't need to assume that your transitions came from any particular policy. You can actually use any transitions you want, and we'll see what that means in a second. There's only one network that's being learned, so you don't need a separate critic and a separate actor network. The downside with this method is that once you start using neural nets in place of tables, unfortunately this method does not converge. That seems pretty bad. It doesn't converge in theory. It often doesn't converge in practice. And for some reason, that doesn't keep us from wanting to use it all the time. So we'll actually find out how to use it properly on Wednesday. Today, we're going to find out why it doesn't converge. But before we do that, I want to summarize the complete algorithm just to put the pieces together. Then we'll take a short break, and then we'll have a somewhat depressing theory component to the lecture where we'll learn that nothing really works. But first, let's talk about what it is that doesn't work. So this is the full fit Q iteration algorithm, and all Q iteration and Q learning methods are essentially special cases of this more general method. So the full Q iteration algorithm works like this. Step 1, you collect transitions using some policy. I'm going to say collect transitions instead of collect trajectories because the algorithm actually doesn't care whether your transitions are grouped into trajectories or not. So all it needs is a collection of S, A, S prime, and R tuples. Now, generally, if you're running a policy in the real world, you're really getting trajectories, unless somebody's like teleporting you to different states all the time. But the algorithm doesn't really care. So long as what comes out is a set of transitions, doesn't care whether they're arranged trajectories or not, just needs to know S, A, S prime, R, and it needs to get a large enough collection of these. So the free parameter is the data set size n, meaning how many of these do you collect. Typically, you need quite a few. And the policy that you use to collect them. And the algorithm is actually pretty flexible about the policy that you use. So it doesn't have to have those transitions get collected with the current policy. And this in particular implies that you can actually use all the transitions you've collected with all of your old policies, and you can aggregate them together. Step 2, construct your target values. So just like for actor critic, we need to construct those regression targets, which we create using a bootstrapped update, plugging in the max in place of v. So before we had that v, that's where the max was hiding. So I'll just write it out here so that it's not hiding anymore so you can all see it. Set your y for sample I to be the reward. That's the one that you get right here, plus gamma times the max over the next action of your Q function estimator evaluated at the next state and the next action. Step 3, supervised regression. Train your value function estimator to regress onto those yi's for every si ai tuple. So there's your Q function estimator. It takes in two things, an S and an A, and it outputs a real value and has parameters phi. So that what you have to choose for step 3 is the number of gradient steps S. And there are interesting algorithms that you can derive as special cases of this if you choose S to be 1 or if you choose S to be very large. And we'll see that after the break. You repeat this process multiple times. Why do you repeat this process multiple times? Well, because doing one step of supervised regression doesn't actually get you an optimal Q function. It just backs up the Q function one step. So you have to repeat this multiple times until the Q function actually converges. If it does, which it won't. So you have to choose the number of iterations, k, before you go back out and collect some more data. And there are some interesting design choices to be made as to how often you go out and collect more data versus crunching some more on the data that you already have. So this is the general design for a fitted Q iteration algorithm, of which Q learning is a particular special case, and there are many other interesting special cases. Does anybody have any questions about fitted Q iteration? OK, so to review what we covered, we talked about value-based methods, which don't learn a policy explicitly. They just learn the value function or the Q function. If you have a value function, you can recover a policy from that value function by using the argmax, as I discussed. You can derive a fitted Q iteration algorithm, which basically uses these ideas and turns them into a method that we can apply on sampled transitions without knowledge of the true dynamics and without assuming that the states and actions are small and tabular. At this point, we'll take a short break, and then after the break, we'll learn about why this method doesn't work. So we'll be back at 10:56. Hello.
I have a question about something that's like sort of related to this.
Mhm.
But I was wondering, I'm currently doing some like single photon imaging. We use
Okay.
NMF, non-negative matrix factorization,
Okay.
to actually like clean the data and figure out which cells are where in
Okay.
this like sequence of video frames.
OK.
And the way that works, like essentially, you're feeding in just like the raw image data. Could you theoretically make features from a neural net, like learn a function to actually put into NMF? Has that been done, or is that not something you're familiar with?
It seems like you probably could. It's not something I'm familiar with.
Okay.
I guess to really answer your question, I probably need to understand the details of that a little bit more,
Yeah.
which is perhaps a longer conversation. Maybe we can talk about that on Wednesday.
Okay. Sounds
But probably, I need to understand it better, though.
Okay. Cool.
Yes.
So so it seems like in value iterations,
Mhm.
you, like you said, you learn. So what you're learning and what you're adjusting are like parameters, or you're approximating like the function used to like give you how good the action is.
Yes.
And then your policy is something that's automatic, which is like take the biggest action.
Yes.
Take the action that gives you the biggest value.
Yes.
But in policy iteration, I know you adjust the parameters of the function used to take to I guess compute your action. But then
So in both value iteration and policy iteration, the only thing you're actually learning is the value function. In policy iteration, it just sort of, they're really essentially almost the same algorithm. It just policy iteration makes it a little bit more explicit that there's this policy extraction step, which you do every time around the cycle. So typically, if you would actually implement policy iteration, you would actually have a table where you would write out what the optimal action in every state is. Like you literally just write in the index of that action, and then you plug in that index next time you do policy evaluation, next time you fit the value function.
oh, except instead of plugging in the value. So,
Yeah.
so then
Whereas in value iteration, you would figure out the max, and then you wouldn't even store the index of that max. You would just directly get its numerical value and plug it in.
Okay. Okay.
Well, one of the ways that you can see how they're similar is if you actually write out the policy iteration algorithm, and then imagine what happens if the policy evaluation step is only done for one iteration. So right, policy evaluation means like you set the value to be the R plus the expectation of the next value. Imagine doing that only once instead of repeating it multiple times.
For the policy.
Yeah, for the policy evaluation step for step one.
But
And if you do that, you get exactly the same form as the value iteration algorithm.
But isn't, I guess I'm trying to see the differences. So it seems like in that step of policy iteration, you're getting like a value that's like how good the action is. So
Yeah, you're getting that in value iteration too. So the reason that it's hard to see the difference is because the difference is very mild, right? So you can basically go from policy iteration to value iteration just by taking that first step of policy iteration where you evaluate v pi. That's an iterative step, so you have to actually repeat that v gets assigned r plus next v multiple times. If you do that step only one time, then the algorithm is the same as value iteration.
Okay, so in that first step, v pi, you're doing it multiple
Yeah.
times to recover
Yeah.
But okay, but VPI is still like a value function and value
Yeah.
is how good.
Right, so in both cases you have a value function,
Okay.
and in both cases that value function corresponds to some policy.
Okay.
It's just that in policy iteration you wrote out that policy explicitly in a table. In value iteration you never actually created that table, but you can always recover it just by taking the max.
Oh, okay, interesting.
So they're very, very similar algorithms.
Okay, I'll try to see it. Thank
Yeah.
you.
All right, let's resume. So in the second half of today's lecture, we're going to talk about why fit acute iteration is an off-policy algorithm and what it means to have an off-policy algorithm, and then we'll learn about why it doesn't work. And then on Wednesday, we'll learn how we can actually make it work. So why is this algorithm an off-policy algorithm? I said this a few times. Off-policy means that step one, where you actually collect your data, doesn't make any assumptions about what policy you actually use to collect that data. So the reason that it's an off-policy algorithm is because the only part of this method that actually uses any assumption about the policy is this max. So this max essentially assumes that your policy is the argmax policy. If your policy is the argmax policy, the value of the argmax policy is simply the numerical value of the max. So this essentially approximates the value of your updated policy pi prime at the state Si prime. The good thing, though, is that if you only want to figure out the value of your new policy at the state Si prime, you have your Q function estimated right there, ready to give you a value, without needing to actually know where you will transition to from taking that next action. So this method doesn't try to figure out where your new policy will get you to go. It just needs to figure out what value it'll get when it goes there, and the value function, the Q function approximator, gives it exactly this value, or at least an approximation thereof. Which means that you don't actually need to know what policy the transition itself came from, because you're not evaluating the value at the state Si, you're evaluating it after taking the action AI in state Si. So this doesn't actually assume anything about the policy that did this. You are assuming that you will take your policy at the state you land in, Si prime, but there you don't actually need to know the transition. There you just ask the Q function estimator for what the value would be. That's very, very convenient. So given S and A, this transition is independent of pi, right? Because pi just determines the A, and if I told you this is the A that you got, now pi doesn't actually influence anything in the transition itself. It only influences what happens when you land at the resulting state Si prime, and there the Q function estimator is ready to give you a value. So no need to interact with the dynamics anymore. So you can conceptually think of fit acute iteration as just assuming that you have some soup of transitions that in effect serve to illustrate to you what the dynamics of the environment are. So that's your data set of transitions. And then you kind of crunch on this data set. You repeatedly perform this fit acute iteration procedure on that data set to get a better and better Q function. In effect, the data set almost acts as a non-parametric model of your system. So it's no longer the transitions are no longer telling you what your policy would have done. They're just there to tell you what the consequences of different actions might be, and then your Q function estimation is what actually takes care of the latest policy. So this is kind of a crude, intuitive explanation for why fit acute iteration is an off-policy method. This is an important idea, and it will continue to come up again and again through today's lecture and Wednesday's lecture. So if anybody has any questions about what it means to have an off-policy algorithm, this is a good time to ask those questions. Yes?
How do we decide when to exit the loop between the bottom two and go recollect our data set?
Yeah, good question. So the question was, how do we decide when to exit the loop between step 2 and step 3 and jump back out to step 1? Another way to phrase this question is, well, if it's an off-policy algorithm, why the heck do you ever need to have this outer loop? Why can't you just collect all your data once at the beginning and then just repeatedly learn on that data? The reason that you might want to come back to step 1 is that your initial data needs to be collected using some initial policy. And if your initial policy is very bad, you might never see some of the interesting states in your system. So if, for example, you're playing a video game and the video game has 10 levels, initially you don't know how to play the video game, so you have a completely random policy. That random policy might never progress past the first level, which means that your data set of transitions wouldn't have any data from levels 2 through 10. So what you might want to do is you might want to actually train a little bit on data from level 1, then actually run that policy to see if it gets to level 2, collect some more data, and then repeat. Otherwise, you might never actually beat the whole game. Any other questions? Okay. All right, so here is maybe a trickier question. What is fit accumulation optimizing? We saw before that policy gradient is optimizing the expected return. So policy gradient is, it's literally the gradient of the expected return, so it's making the expected return bigger. We saw that actor critic was another way to approximate the policy gradient, so that was also optimizing the expected return. What the heck are we optimizing in fit acute iteration? Yes? We're minimizing Bellman error. That's interesting. So what is Bellman error? Bellman error is E. Bellman error is this thing. So when someone says Bellman error, what they mean is the difference between the left-hand side and the right-hand side. So basically the q minus the y. And here I can substitute in the equation for the y. It's just r plus the next q. So this is the definition of Bellman error. It's basically the difference between your target values and your current values. We are indeed minimizing Bellman error during one step of the fit acute iteration procedure, during step 3 in particular. But we're not really doing that when we do step 1 or step 2. In fact, step 2 usually makes the Bellman error bigger. Is there anything else that we might be optimizing? So the answer is that nobody really knows. And that's kind of the bad news. When we run Q iteration, not fit acute iteration, but regular Q iteration, we do indeed minimize Bellman error, which is not by itself a virtue, but there is something that we do know, which is that if your Bellman error is equal to 0, then that means that your Q function is equal to the reward plus the max over the Q value at the next state, which actually means that your argmax policy has converged. It means that when you evaluate the Q value for the argmax policy, you get the value that you already have, which means that your policy cannot be made any better. Remember that when you do the argmax policy, it makes your policy at least as good as the previous one. If the left-hand side is equal to the right-hand side, that means that the argmax policy is equal in value to your current policy, which means that it can't get any better. And you can actually prove that this means that your policy is optimal if you have a tabular representation, meaning no function approximation error. So if the Bellman error is 0, you have what we call an optimal Q function, which corresponds to the optimal policy, which you recover by doing the argmax. So getting Bellman error to 0 is great, because that means that you got the optimal policy. Getting Bellman error to be smaller than the previous Bellman error, I don't know. I don't know what that does. Seems to work in practice. So you can maximize reward if you get it to actually be 0. And sometimes we write the optimal Q function, the one that actually has Bellman error equal to 0, as Q star, and we write the optimal policy as pi star. So if someone says, I have the optimal value function or I have the optimal Q function, what they really mean is I have the value function or the Q function that corresponds to the optimal policy, which is pi star, which is the policy that gets the largest reward. And the optimal Q function, Q star, satisfies this equation. It is equal to r plus gamma times the max of the Q value at the next state for all states. Most guarantees are lost when we leave the tabular case, for example, when we use neural networks for function approximation. We can also derive an online version of the Q-learning algorithm. So just like we derived an online version of actor critic last week, we can make Q-learning online. That's actually pretty easy. So here is the full fit acute iteration algorithm. The online version is a special case of that method. In the online version, step 1 is to take some action AI and observe the transition Si AI Si prime Ri. Step 2 is to compute the target value for that single transition. And step 3 is to take one gradient step on the difference between the Q value at Si AI and the target value Yi that you just computed. So this is a fully online algorithm, meaning that it just takes one gradient step every single transition, doesn't store any transitions, and just happily chugs along like this. It is a special case of the full fit acute iteration algorithm, where in step 1 you collect only one transition, and in step 3 you take only one gradient step, and you alternate steps 2 and 3 only once. So you basically set all of the hyperparameters to 1, and you get fully online Q-learning. So step 1 now is actually off policy. So for actor critic, step 1 needed to be taken using our actual current policy. Here, step 1 can be taken using any policy, and you still get a valid algorithm. In practice, this is, of course, not a good idea for the same reason that the vanilla online actor critic algorithm was not a good idea, which is that in step 3, you're only taking a gradient step on one single data point. So in deep learning and in general in machine learning with high-dimensional parametric function classes, we prefer to use mini batches of size more than 1, and this, of course, has a batch size of 1, which is not going to be very stable. We'll come back to how to fix that on Wednesday. One thing I want to discuss a little bit before we dive into more of the theory is something I've said a few times already, which is the choice of policy in step 1. So I keep saying that you can use any policy you want for step 1, but an obvious question is, well, which one should we use? So which policy should we use for step 1? Well, we could use our final policy. So we could basically take our latest Q function and we can we can basically extract the pi from it. We can say, let's take the action with probability 1 if it's the argmax. Is this a good idea? Should we do this? Any ideas about why this might be good or not good? Yes, over here.
If we have an inaccurate Q function estimator, then we may never see states that are actually good.
Okay. So one answer is maybe you don't want to use this particular pi in step 1 because if you have an inaccurate Q function estimator, maybe you haven't finished learning yet, then you might do some pretty useless stuff in step 1 and never see any of the interesting states. Any other hypotheses about why we may or may not want to use this particular policy in step 1? Yes, over here.
No, you might not explore.
You might not explore very well. So this is a deterministic policy. Remember, when we were doing policy gradient, we had a stochastic policy. In fact, when you actually go to implement policy gradient for your homework, you could try to play around a little bit with the initial variance of your policy for continuous actions or the temperature of the softmax for discrete actions and see how that affects learning. And what you'll probably find is that having that policy be highly stochastic at the beginning is quite important because that highly stochastic policy will try lots of different things and as a result randomly discover high reward regions. This policy is always deterministic, which means that if your initial Q function is bad, which it has to be because it hasn't been trained yet, then this deterministic policy will do the same thing every time. It will probably do some highly inadvisable thing, which means that it will probably not see high reward regions, which means that you will not learn how to reach those high reward regions because you don't even know that they exist. So what we want to do in Q learning is we want to select the policy for step 1 that is usually a bit more random than just the deterministic argmax policy. So we have a few choices. One choice, which is very simple to explain but a little hard to write out, is called the epsilon greedy policy. So the epsilon greedy policy is in some sense the simplest kind of exploration method you could have. It says every action has a non-zero probability, but the best action has a higher probability than the others. And specifically, every action has a probability, specifically you have a 1 minus epsilon probability of taking the best action, and then the remaining epsilon you divide up evenly among all the other actions. So you say for every action it has at least some probability, and we'll just say it's uniform over all the actions except for the best one, which has a probability of 1 minus epsilon. And you choose epsilon to be some small number, so that the larger the epsilon is, the more random you behave. For a small epsilon, you're mostly going to be taking your best action. For a large epsilon, you're mostly going to be doing random stuff. Another choice is to use what's called a Boltzmann exploration strategy. So the Boltzmann exploration strategy is a little bit more informed by your actual Q values. It says, let's take actions in proportion to some positive transformation of Q values. Probabilities have to be positive, so you have to do some positive transformation. And exponential transformation can work pretty well because when you exponentiate a bunch of numbers, you know that they're going to be positive. And this strategy tends to bias you away from the actions that you're sure are bad. So if you have some actions that have a really negative Q value, they'll get a really low probability of being taken, whereas this thing will give all the suboptimal actions equal probability. We'll discuss a little bit more some of the mathematical reasons why we might prefer one or the other when we discuss control as inference and other exploration strategies towards the second half of the course. But for now, as a general rule of thumb, if you're not sure what to do, epsilon greedy is a pretty simple and straightforward choice. If you want to do something a little fancier, or if you have a very large or continuous action space, or if you have some actions that you really don't want to take because they're bad, then maybe consider Boltzmann exploration. All right, to recap, we talked about value-based methods that don't learn a policy explicitly. They just learn a value function or Q function. You can recover your policy from the value function. You can set up fit-a-Q iteration. Fit-a-Q iteration in the general setting is a batch mode off-policy method, although you can instantiate it as an online method, which is the Q-learning algorithm. So the Q-learning algorithm is basically the online analog to fit-a-Q iteration, which we saw as a special case when we set the number of transitions that we collect to 1, the number of gradient steps to 1, and the number of evaluation iterations to 1. So let's talk a little bit about the theory. In order to analyze the value iteration and Q iteration algorithms, I'm going to first introduce a little bit of notation. So this is the value iteration algorithm that I had before. This is the one that requires us to know the transition dynamics and keep tables and all that stuff. And I'll start with it because it's a little bit easier to analyze. So this is the case where we have a small state space and we have a number for every single state. So the first question I'll ask is, does value iteration converge? To study the convergence properties of value iteration, well, of course, if it converges, we need to know what it converges to. To study the convergence properties of value iteration, we'll first simplify our notation a little bit by defining this Bellman backup operator. So B is an operator that is defined like this. It operates on a value function. And remember, a value function is a table. So in a sense, I can represent it as a vector. It's just a vector of numbers. So you can view it as an operator that operates on this vector. And what it does is it takes a max over the actions. And then inside that max, it has the reward for that action plus gamma times the transition matrix for that action times the old value function. Representing value functions as vectors and representing rewards for a particular action as vectors, this is basically an expression in terms of linear algebra. So this is a stacked vector of rewards at all states for action A, and TA is just a matrix. It's a matrix where every entry represents the probability of landing in a particular state I, given that you were previously in state J and took action A. So since A is a subscript of T, this is now, T subscript A is not a tensor anymore, it's just a regular old-fashioned matrix with dimensionality equal to the number of states by the number of states. So if V is a vector, T is a matrix, T times V is also a vector, R is a vector, so this is a well-formed linear algebra expression. You evaluate this for every possible action, so you get a bunch of vectors, one for every action, and then you take an element-wise max. One of the things that you can show is that the optimal value function, V star, is a fixed point of B. What does it mean for a vector to be a fixed point of an operator? It means that when you apply that operator to that vector, you get back that same vector. So, well, what's the optimal value function? Well, the optimal value function is just the one that's equal to the max over the actions of R plus the next V. It's also the value function for the optimal policy. So of course, if the left-hand side is equal to the right-hand side, then directly from the definition of B, that means that V star is equal to BV star. So that's nice. We know that this operator has a fixed point, which is the optimal value function. Now, the real question is, does it converge to that fixed point? So we know that if we get to V star, we'll stay at V star. Do we actually get to V star? So the fixed point always exists. It's always unique. I haven't proven that, but I'll leave this as an exercise for you. And it always corresponds to the optimal policy. So will we reach it? Here's a sketch of how we can study this question. Again, what I'll show next is not a full proof. It's just a sketch, but you can go through the proof on your own. It's actually not very complicated. So we can prove that value iteration reaches V star because B is a contraction. What does it mean for an operator to be a contraction? It means that for any V and V bar, so these are for any two vectors essentially, for any two vectors, the difference between the vectors you get by applying B to both of them, so the difference between BV and BV bar, is less than or equal to gamma times the difference between V and V star. So we call this a contraction, which means that after you apply b to both of the vectors, they get closer together. Hence contraction. Now, something important to note here is that the difference here is quantified in terms of the L infinity norm. That is the difference for the entry that has the largest difference. This is going to be important later, the particular choice of norm here. This norm is the infinity norm. And the contraction is by some factor, and it turns out that factor is actually gamma. The factor is the discount factor. A little bit of intuition for why this is true. If gamma was equal to 1, then these value functions would essentially be infinite sums. So big infinite vectors aren't going to be getting any closer to each other. So as gamma approaches 1, the contraction factor gets closer and closer to 1, which means that once it's actually 1, it's not a contraction anymore. But for any value of gamma less than 1, the vectors get closer together. If we know that b is a contraction, we can actually immediately recover a proof of convergence for value iteration. In order to recover a proof of convergence for value iteration, we simply use the fact that v star is a fixed point of b. So if we choose, let's say, v bar to be v star, then bv star is equal to v star, right? That's what the fixed point means. So if you substituted in v star for v bar in this equation, then on the left-hand side, bv bar will just become v star, right? Because bv star is equal to v star. So from the definition of a contraction and the knowledge that v star is a fixed point of b, we recover this equation at the bottom. bv minus v star is less than or equal to gamma times v minus v star. What that implies is that if you apply the operator b to any vector v, it'll become closer to v star in terms of the infinity norm. And it will become closer by some amount that is quantified by the discount factor gamma. So some non-negligible amount. So from this, you can actually get a proof of convergence. You know that if you apply this operator enough, it'll get closer and closer to v star, and will eventually reach v star if you have no function approximation error, meaning that you're storing your value function in a table, and all possible value functions, all possible vectors v, can be represented by that table. So that means that every time you take a step with value iteration, the blue dot, which represents your current value function v, moves closer to the yellow star, which represents v star, and eventually reaches it. And then you're quite happy with this because now you have the optimal value function, and that means you can recover the optimal policy. Okay, does anybody have any question about this derivation? Yes?
You use the discount factor, and you say that the amount that the new value function approaches the optimal value function is related to that. But it seems from that inequality that you maybe can say it's proportional to it, but not necessarily. You can't say objectively how close you'll actually get or how quickly it will converge.
So what you can say from this equation is that the distance to the optimal value function, the infinity norm, will decrease by a factor gamma. Right? Gamma is less than 1, so if you take a factor that's less than 1, you raise it to a large enough power, eventually it gets arbitrarily close to 0. And this is important because if this number wasn't there and you just had a less than or equal to sign, then maybe this process would stall. Maybe eventually the distance between v star and v would decrease by such negligible amounts that it would never actually reach it. But because you know that there's a factor less than 1 out front, that factor raised to a large enough power will be arbitrarily small. So for any small enough constant, I can pick a number of iterations such that I will be within that small constant of the optimum. Yes?
Two questions. First, so is this a motivation for why we use discounting? And second, what happens in the undiscounted case?
Right, so the question is this a motivation for using discounting, and what happens in the undiscounted case? It's a good question. The reason I'm hesitating is because I think you can probably derive some algorithm that recovers a value function in the infinite horizon average reward case, but I don't know how to do that right now. So maybe this is a good question to ask me next time once I've had some time to read up on this. Yeah, I don't really know the answer to that. Okay. All right, now let's get to the fun part. Non-tabular value function learning. This is what we really want to do. We want to not have to store a full vector of values in every single state because we might have an enormous number of states. We want to use some kind of function approximator. So here's our fitted value iteration algorithm. And the first thing we're going to do is, in order to do some analysis, we need to declutter our notation. We need to introduce some simpler notation to explain what's going on because, when we're doing theory, we're lazy and we don't want to write lots of equations. So let's talk about that second step. That's the new thing, this argmin. What is this argmin doing? One way that we can view the argmin is as an operator that finds a value function in some set of value function omega that minimizes the difference between the value function you're finding and the backed up version of the previous value function. So you can think of your training data as being the backed up version of your previous value function, and what you're doing is you're searching for some other value function in some set that minimizes this difference. So here, when I write v and v prime, these you can think of conceptually as big vectors with numbers for every state. But our vectors are now constrained to lie in some set omega, which might be, for example, the set of all value functions that can be represented with neural nets that have 2 layers and 370 hidden units, right? So this is our class of hypotheses, and we're finding the closest fit to our backed up value function in that hypothesis class. So omega might be the, all value functions represented by a neural net. You can think of this visually like this. Let's say that this line represents omega. So the line represents all vectors that can be represented with neural nets. It's not actually a line, but I'll draw it as a line just to keep it simple. The dot here represents our old value function v. When we apply the Bellman backup, which is what's going on when we calculate these y's, we're finding some new value function bv, which lies off of this manifold. So bv may not be possible to represent exactly using a neural net. When we perform this argmin, what we're doing is we're finding the closest neural net, meaning the closest value function that lies on this line, to this bv. Now, when we do empirical risk minimization, when we do essentially supervised learning, we use some norm here. Typically, it's the L2 or L1 norm. It's generally not possible to do this with the L infinity norm because that requires finding the most violated entry. So it's going to be something like L1 or L2 norm. Let's go with L2 norm because that one is simplest, but the same thing will be true for L1 norm as well. So L2 norm means that you basically want to find a v prime where this line will be at a right angle to your manifold, right? You want to find the closest projection. So that means we can define a new operator. We're going to call this operator pi, not to be confused with a policy. So pi v is just this argmin operator. And the reason I called it capital pi is because it's a projection operator. Because if you use L2 norm here, that means you're projecting bv onto the manifold omega. You're finding the closest v prime to bv, which is going to be the one that's at a right angle to this vector. So it's a projection operator. And if I'm using squared error here, then it's a projection in terms of the L2 norm. And this little detail, the fact that it's L2 norm, will be important. So now I can finally do the thing that I promised all along, which is write the fitted value iteration on one line. I can just write it as v becomes pi bv. Very simple. Unfortunately, this seemingly, yes, question.
Oh, sorry. Why are we trying to minimize a projection of like the updated value function and not its projected like I guess version instead of like minimizing maybe the distance between two different steps in the value function?
So the question is, why are we trying to optimize for projection? So what we're really doing is we're doing this. We're doing step 2. Whenever you do supervised learning, you can view supervised learning as finding a function in a function class that is the best possible fit to your data. That's essentially what supervised learning does. So omega here is your function class. V prime is your function. And you're finding the V prime that is the best fit to your data. So the best fit to your data, you can view it as following. There's some true function that generated your data. You can't represent that true function, so you find the closest thing to it in your set of functions omega. And that operation of finding the closest one is a projection operation. Any other questions? OK. So far we've greatly shortened our equation, but we haven't actually reached any conclusion. So here's what we know. We know that B is a contraction with respect to the infinity norm. The infinity norm, you can think of it colloquially as the max norm. It's basically the difference between the two entries that have the largest difference. So mathematically, you can express it like this. BV minus BV bar under the infinity norm is less than or equal to gamma V minus V bar under the infinity norm. That's great. That lets us show that value iteration converges. Projection is a contraction with respect to the L2 norm, or Euclidean distance. This is pretty easy to imagine geometrically, because if you imagine that these are your 2 points, V and V bar, when you project those 2 points onto a line, they can only get closer together. They might not get closer together. They might stay the same exact distance apart, but they'll never get further apart. So any L2 projection is a contraction. Now, its constant is 1. That's not great, but it's still a contraction. They're not going to get further away. So you might think, well, this is a contraction with a constant less than 1. This is a contraction. So surely composing 2 contractions together gives you a contraction. Unfortunately, it doesn't. And the reason that it doesn't is because of that annoying L infinity and L2. They're contractions in different norms. And if you compose contractions in these 2 different norms, you actually get something that is not a contraction of any kind. So back when we had B times V, we had this nice picture where we go directly to the optimum. Now here's what we've got. Let's say this is our V star. This is our current V. Apply the operator B. B moves us closer to the optimum with respect to the infinity norm. So now those of you that have are kind of in the habit of imagining geometric transformations in your head, you can look at this picture and imagine what happens when we project BV onto the line omega. Projecting BV onto the line omega means you take a line at a right angle and you get this thing. And this is further from V star than you started. In fact, if you keep going, you will get quite far away. So fitted value iteration might not converge, and it might actually move you further away from the optimum. So conclusion, value iteration converges in the tabular case. Fitted value iteration does not converge. It does not converge in general. It does not converge often in practice. The same exact thing applies to fitted Q iteration. I'm out of time for this lecture, so I won't go through it in detail, but it's exactly the same argument, which means that online Q learning doesn't converge. That's very unfortunate. So I'll leave you on this somber note, and then on Wednesday I'll tell you how we can actually implement practical and very effective deep learning algorithms based on this principle.
I had a quick question about your last slide. Do you know if this relationship holds whenever you apply a smaller p-norm to a larger p-norm, as we're doing here? Or would it be a contraction in the norms?